Hello, this is Richard Hammack's Calculus 1 course. We're in part 5 of the course on integration. Our previous lecture introduced the fundamental theorem of calculus. It came in two parts, part 1 and part 2. It's a significant theorem, and there's a lot to be said about it. Today's lecture 44 is on working with the fundamental theorem. Our plan is to, first of all, review and further develop the fundamental theorem of calculus part 2. Then we'll look at examples for the fundamental theorem of calculus part 1. We'll discuss even and odd functions, a topic that you may have seen in a previous course, perhaps an algebra course. It takes on an added significance in the context of definite integrals, as we'll see. And we'll look at the average value of a function, which is an interesting and useful interpretation or application of definite integrals. But before doing all of this, I want to take a few minutes to say some words about the notation that we've been using and that we'll continue to use. Remember that the definite integral from a to b f of x dx is defined to be a number that's equal to this limit. The limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k delta x with the usual interpretation. And as we know, this sum that occurs here is called a Riemann sum. So the definite integral is a limit of Riemann sums. This elongated s that occurs here, that's called the integral sign. And you can look at it as being a streamlined version of this sigma. The limit as n goes to infinity of the sum from k equals 1 to n. Think of it as representing that. The a is called the lower limit of integration, and the number that's up here at the top is called the upper limit of integration. And collectively, these numbers are called the limits of integration. And I'm mentioning this because the words that we're discussing here will come up in the textbook and also during lecture. And so we should at least acknowledge them. This function f of x, which you can think of as being a streamlined version of the f of x sub k, that's the function you're integrating. It's called the integrand. And this dx, it's actually a differential. We talked about differentials in part 4 of the course. And there's a significance for having a differential there. It actually is packed with meaning, but its meaning really emerges in calculus 2 and calculus 3. I think for calculus 1, it's best just to look at this dx, not so much as a differential, but a closing punctuation mark for this definite integral. Don't forget to write it. It's part of the notation. It's like a period. It's part of the syntax. It just closes off this definite integral. You can look at it perhaps as a streamlined version of the delta x that occurs here. Since this definite integral is actually equal to this limit of Riemann sums, the dx could be looked at as a holdover from the delta x. But as you go on, you'll see a deeper meaning to that differential, but don't worry about it too much for now. So with this, let's move on to our lecture. Let's tackle the first task. You'll remember that the fundamental theorem of calculus, part 2, states that if f is continuous on the closed interval from a to b, and big F of x is any antiderivative of little f of x, then the definite integral from a to b of little f of x dx equals big F of b minus big F of a. And we also introduced this piece of notation, which we read as big F of x from a to b, and that's just a abbreviation of the expression big F of B minus big F of A. So whenever you see this, the big F of X from A to B, it stands for big F of B minus big F of A. We looked at some examples of the fundamental theorem of calculus part 2 last time, and we'll continue with that. How about the integral from 1 to e of 1 over x dx? Well, the fundamental theorem of calculus part 2 says that this definite integral is going to be equal to an expression that is as simple as finding an antiderivative of 1 over x, which is, as we know, ln of x. So the fundamental theorem of calculus part 2 says that the integral from 1 to e of 1 over x dx is ln of x from 1 to e. And that would be ln of e minus ln of 1, and ln of e is 1, and ln of 1 is 0. So we get 1 minus 0, and an answer of 1. So the definite integral from 1 to e of 1 over x dx equals 1. You could think about that, if you like, in terms of area. Here's the graph of f of x equals 1 over x. And we're looking at the definite integral from 1 to e. Here's 1. And e is like 2.71828. So it's a little bit bigger than 2. The fact that we got 1 in this definite integral says that this shaded region has an exact area of 1 square unit. Next example, the integral from 1 to 2 of 3x squared plus 4x minus 1 dx. So the fundamental theorem of calculus part 2 says that all we need to do to find that definite integral is to look for an antiderivative of 3x squared plus 4x minus 1, and then go from 1 to 2. And you can work out this antiderivative in your head piece by piece. An antiderivative of 3x squared would be 3x cubed over 3. An antiderivative of 4x, let's see, that would be an antiderivative of 4x to the power of 1. By the power rule for integration, that would be 4 times x squared over 2. And then minus an antiderivative of 1, which is simply x. So there's our antiderivative, and we evaluate from 1 to 2. And we'll do some cancellation where possible here. So do the cancellation and evaluate from 1 to 2. If you plug in 2 to this expression, you get 14. If you plug in 1, you get 2. So 14 minus 2 is 12. So that's the value of this definite integral. Here's another one. The integral from negative 1 to 1 of 1 over 1 plus x squared dx. Fundamental theorem of calculus part 2 says that the answer is going to be this. You look for an antiderivative of 1 over 1 plus x squared, and we know that's tangent inverse of x, and you evaluate from negative 1 to 1. So that's tangent inverse of 1 minus tangent inverse of minus 1. Well, tangent inverse of 1, that's pi over 4. Tangent inverse of minus 1 is negative pi over 4. So in our answer, we get pi over 2. Let's try another one. The definite integral from 0 to pi cosine x dx. Well, the fundamental theorem of calculus part 2 says that this is just going to be an antiderivative of cosine of x from 0 to pi, and an antiderivative of cosine of x is sine of x. Because if you take the derivative of sine of x, you get cosine of x. And remember, we don't need to use the plus c here because we can take any antiderivative. So we just have c equals 0. So instead of sine of x plus c, just sine of x. Plug in pi, minus plug in 0. That's sine of pi minus sine of 0. And sine of pi is 0, and sine of 0 is 0. So our answer here is 0. The definite integral from 0 to pi at cosine x dx equals 0. Now that answers the question, but it just so happens I have a little room here where I could put in a graph. And if you think about the graph of cosine of x between 0 and pi, you understand why you got a value of 0 for this definite integral. It's because part of cosine of x is above the x-axis, and right here at pi over 2, it switches and becomes below the x-axis. And it's really easy to believe that the a up minus the a down is going to be 0, that these two regions have the same area. And this area minus that one, a up minus a down, which we know is the value of this definite integral, would be 0. So the answer makes sense. Next, we're going to talk about an interesting interpretation of the fundamental theorem of calculus related to rate of change. To describe it, let me paraphrase the fundamental theorem this way. If big F prime of x equals little f of x, in other words, if big F is an antiderivative of little f, then the integral from a to b of little f of x dx equals big F of b minus big F of a. In this setup, the integrand little f of x equals big F prime of x, so we can write this as the integral from a to b of big F prime of x dx equals big F of b minus big F of a. Remember that the derivative big F prime of x has an interpretation as the instantaneous rate of change of the quantity big F of x at x. And in that context, this integral on the left becomes the integral from a to b of the rate of change of the quantity big F of x dx. And it equals big F of b minus big F of a, the quantity at b minus the quantity at a, which you can regard as the net change in the quantity between x equals a and b. As an example of this, imagine a situation where you have water gushing out of a pipe into a reservoir. And here we'll use the variable t for time rather than the variable x. Consider the function r of t, which is the number of gallons per minute of the water flowing through that pipe at time t. And let's say that t is the number of minutes after midnight on a particular day. So r of t gives the instantaneous rate of change of water through that pipe at time t. So for example, at time t equals 35, say, water may be gushing out of this pipe at a rate of change of 375 gallons per minute. And at some other time t, it may have tapered off to a trickle. The instantaneous rate of change might be 0.5 gallons per minute of water through the pipe. R of t gives the instantaneous rate of change of gallons per minute of water coming through that pipe at time t. And that's a rate of change. You might look at it as the rate of change of the quantity which equals the amount of water that has come through that pipe at time t, the amount of water since midnight. Let's think about, say, the integral from 5 to 10 of r of t dt. R of change is the rate of change of a quantity, the rate of change of the number of gallons that have come through that pipe since midnight. And according to this interpretation, the integral from 5 to 10 of this rate of change would be the net change in the quantity between a and b. In this case, the net change in the quantity between 5 and 10, which would be the number of gallons of water that have come through that pipe between 5 minutes past midnight, and 10 minutes past midnight. Here's another example. A ball dropped off a bridge at time t equals 0 has a velocity of minus 32t minus 5 feet per second at time t. It hits the ground when t equals 2. The question here is, how high is the bridge? So you'll recognize this problem as something that you could solve as an initial value problem that we talked about a number of lectures ago. But you could also look at this in the context of this new interpretation of a definite integral. To see how, think of it this way. Think of the change in the ball's position between times t equals 0 and times t equals 2. That would be the height of the bridge, how much that ball has changed. The velocity function that's given here is the rate of change of the ball's position. So consequently, the net change in the ball's position would be the integral from 0 to 2 of the rate of change of that position, which is the integral from 0 to 2 of minus 32t minus 5 dt. And you can solve this integral using the fundamental theorem of calculus, and you'll get negative 74. So the net change in the ball's position between the time it was dropped and the time it hit the ground was minus 74 feet. That's negative because the net change was negative. The ball went down. And that tells us that the bridge is 74 feet high. So read about this interpretation of the fundamental theorem of calculus in terms of rate of change, and maybe work a few exercises. Now, continuing with our plan, we said we would review the fundamental theorem of calculus part 2, which we just did. And I want to now go on to the fundamental theorem of calculus part 1. And you'll remember that this is the one that says that if f is continuous on the closed interval from a to b, then the function a of x, which is the integral from a to x f of t dt, it's differentiable on the open interval from a to b, and in fact its derivative is this, d dx of the integral from a to x f of t dt simply equals the function f of x, the function you were integrating. And here's the picture. You might think of it this way. You got your interval from a to b. You've got the graph of a function f of t. And you pick a value of a x, a t value, x, between a and b. And at least if the graph of f of t is positive, this integral from a to x f of t dt is the area under the curve. And you can see that that shaded region, its area is going to depend on what x is. Bigger for bigger values of x, smaller if x is closer to a. So that's a function of x. The fundamental theorem of calculus part 1 says that its derivative is just f of x. It's really simple. So I want to take a look at an example of this, or several examples. Think about the function integral from 0 to x cosine t dt. So that's a function of x. Its value depends on x. And so you could think about its derivative, d dx. And you can tell that the fundamental theorem of calculus, part 1, is going to say that the answer is going to be, instead of your f of t, f of x. So instead of f cosine of t, the answer is going to be cosine of x. But I want to work this out a different way, because we can actually work out the integral from 0 to x of cosine t dt. So before taking the derivative, using the fundamental theorem of calculus part 2, the integral from 0 to x cosine t dt is sine of t from 0 to x. And You'd plug in your x minus sine of 0. That's the fundamental theorem of calculus part 2. So you're here taking the derivative of sine of x minus sine of 0. Now sine of 0 is just 0. So you have sine of x minus 0. So it's just the derivative of sine of x. And we know the derivative of sine of x is cosine of x. So look at the way that worked. The derivative of the integral from 0 to x cosine t dt equals cosine x. It's exactly what this says. The derivative of the integral from 0 to x f of t dt equals f of x. Instead of a f of t, we had a cosine t. Instead of an f of x, we have a cosine x. So this is an illustration of how this fundamental theorem of calculus part 1 is working. Well, if you can always do it this way, then why do you need the fundamental theorem of calculus part 1? Can't you just work out this definite integral and then take the derivative of that? Well, you could, except that sometimes you'll have situations where this definite integral is extremely difficult to work out. So, for instance, look at this problem. Here we have a function, which is the integral from 0 to x of ln 1 plus t to the 6 cosine t divided by t to the 11 plus e to the t. Now, I intentionally made that function as difficult as I could make it. So for any x value, the value of this function that we're differentiating is the integral from 0 to x of all of this stuff, dt. Now, if we were to try to do this one the way we did in the previous example, we'd be trying to use the fundamental theorem of calculus part 1 for this. And the problem is you're just not going to be able to find an antiderivative of this function, so this function of t. So you're at an impasse. However, all we want is the derivative of this function. The problem didn't say we had to find out what this function was exactly, just what is its derivative. And the fundamental theorem of calculus part 1 says its derivative is just going to be f of x. In other words, the derivative of this function is just the integrand with the t replaced by an x. It wasn't that easy? Here's another example. The integral from x to 2 of t sine t e to the t dt. Now, this is not a quite exact match to the fundamental theorem of calculus part 1 because in part 1 the variable is up at the top, the upper limit of integration, and you had a constant at the bottom, and this is flipped around. So before we can apply the fundamental theorem of calculus part 1, we have to put this integral into an applicable form. So we could do that by interchanging the two limits of integration before we differentiate. And remember, when you interchange the x and the 2, you bring one to the top and take the other to the bottom. Remember how that changes the sign? We talked about that in, I think, section 5.2. So now we're looking at the derivative of negative integral from 2 to x, t sine of t divided by e to the t dt. And if you just neglect that negative for a minute, that's a perfect match for the fundamental theorem of calculus part 2. And by the constant multiple rule, we could move that negative outside the ddx, and we have the derivative of integral from 2 to x, t sine t over e to the t dt. And the fundamental theorem of calculus part 2 says that that derivative is going to be what you get when you replace the t's in the integrand just with x's. So x sine of x over e to the x. And then we have this negative that comes along for the ride. So there's your answer. Okay, here's another question. Suppose you wanted the derivative of the function integral 0 to x squared plus x t cosine t dt. What would that be? Now, let me pause for a moment and just point out that if you look at this expression inside the square brackets, this expression that we want to differentiate, its value depends on what x is. For, like, if you had x equals 3, you'd have the integral from 0 to 9 plus 3, the integral from 0 to 12. Whereas if x was 1, you'd have the integral from 0 to 2. So this definite integral depends on the value of x. So it's a function of x. And we're asking, what is the derivative of that function? Well, that's not quite an exact match to the fundamental theorem of calculus part 1 because it just has a plain old x here and not an x squared plus x. So what are we going to do? This is actually, it's like a chain rule problem. You want to find the derivative of the function y equals integral from 0 to x squared plus x, t cosine t dt. You could break that into a composition. It's y equals the integral from 0 to u of t cosine t dt, where that u, that upper limit of integration, it's the function x squared plus x. So in this example, we're looking for the derivative of that function. We're looking for dy dx. And the chain rule says that's dy du times du dx. Okay, let's see if we can compute these individual derivatives here. Well, the du dx, the second one, is the derivative of u equals x squared plus 2. Oh, that's easy. That's going to be 2x plus 1. That's what the du dx is. Now, what about the dy du? That's the derivative of this function. It's like the dy dx, that's the derivative of this. That would be like d dx of the integral from 0 to u t cosine t dt. According to the fundamental theorem of calculus part 1, that would be f of what this upper limit of integration is. In this case, u. So dy du, according to the fundamental theorem of calculus part 1, should be u cosine u. So let's carry that out. Dy du is u cosine u. Du dx is 2x plus 1. And we're almost done. The only thing that remains to be done is we want all x's. So remember, u is equal to x squared plus x in this setup. So these two occurrences of u have to be changed to x squared plus x. So there we go. The first u becomes x squared plus x. Then we have cosine of the second u. That's cosine x squared plus x. And then our 2x plus 1. So the derivative of integral from 0 to x squared plus x, t cosine t dt, is what's in the box down here. There's our answer. So this is going to conclude our recap and examples of the two versions of fundamental theorem of calculus. And I want to emphasize that we started with the fundamental theorem of calculus part 1, and we looked at some examples, and then we moved on to these problems involving the fundamental theorem of calculus part 1, where we are looking at derivatives of these functions defined in terms of antiderivatives, or in terms of definite integrals. These latter ones that we looked at with part 1 of the fundamental theorem of calculus, you tend not to use them as much as you use the fundamental theorem of calculus part 2. And maybe that's refreshing to hear because you really have to sort of pause and think for some of these examples, like the one we just looked at. But for the most part, you'll be using part 2 of the fundamental theorem of calculus. Okay, we're going to move on to our next topic in our list of topics, even and odd functions. I want you to remember from algebra that we call a function f of x even if it happens that f of minus x equals f of x for all x in the domain of that function. So for example, here's an even function, this parabola. Notice that if you took an x value and you look at f of x, in this example, it's exactly what you would get if you took negative x on the other side of the x-axis way over here and took f of minus x. It's actually equal to f of x. And if that's true for all x in the domain of the function, we call this function even. Even functions, they're symmetric with respect to the y-axis, that if you folded the piece of paper that it's drawn on across the y-axis, the two halves of that graph would match up perfectly. So examples of even functions are f of x equals x squared, like the one we see here. Functions that are polynomials, that are powers, sums of even powers, are even functions, as you'll recall. F of x equals cosine of x is an even function. Cosine of x is symmetric with respect to the y-axis. Cosine of minus x equals cosine of x. So cosine of x is an even function. And the reason we're talking about this is that these even and odd functions come up with definite integrals from time to time. There's also an idea of an odd function. A function f of x is odd if f of minus x equals negative f of x for all x in its domain. Almost the same definition of even, except there's a negative right here. So a typical example of an odd function might be like x cubed. Here's the graph of x cubed. And you'll notice that for such a graph, if you take an x value and look at f of x, it's way up here. And then you look at negative x, which is way over here, and take f of that. Here's f of minus x. And this f of minus x is negative the value of f of x. So odd functions are symmetric with respect to the origin. If you took a point x, f of x, on a graph of an odd function and drew a line straight through the origin, an equal distance to the other half of the graph, you'd get to the point negative x, negative f of x. And examples of odd functions are f of x equals x cubed, like the one we see here. Sums of odd degree powers are odd functions. And if you took cosine of x, which was an even function, and you multiplied it by the odd function x cubed, you can check that that's also an odd function. So we see some examples here of even functions and some examples of odd functions. And there are many, many others, of course, that we could add to this list. And I should point out that most functions are neither even nor odd. These are, like most real numbers are neither even nor odd. Like pi is neither even nor odd. Same with functions. If you took like x squared plus x cubed, that's neither an even function nor an odd function. Neither of these two properties hold. But if you have a function that happens to be even or odd, then that says particular things about definite integrals. On one hand, if f of x is even and a is just some number, then the integral from minus a to a of f of x dx is 2 times the integral from 0 to a f of x dx. And I'm going to illustrate that from the shaded regions on this graph. The integral from negative a to a f of x dx would be going from negative a to a. And if we think about that in terms of area, that's the area of this shaded region altogether. Whereas the integral from 0 to a f of x dx is just this area. So it's pretty clear that the entire shaded area is equal to 2 times this half of the shaded area, which means the integral from minus a to a f of x dx is 2 times the integral from 0 to a f of x dx. Now, maybe in Calc 2, you will need to apply this property from time to time. But I'll be the first to admit that it's probably not the most important property out there. It's just exploiting the symmetry of even functions and converting a perhaps more complicated integral into something that's slightly simpler. But the corresponding result that we get for odd functions is actually a little bit more useful. If you think about a function f that's odd, what would the integral from minus a to a of f of x dx be? Well, a up minus a down. And since you're going from minus a to positive a, these two a up regions, the a up and the a down, they're equal in area. So a up minus a down would be 0. So unlike the previous box over here, in this case for odd functions, we actually get a value for the definite integral. It's 0. Now, of course, for that to work, you have to have the lower limit of integration be negative what the upper limit of integration was, which is a bit much to ask in many cases. However, this boxed equation right here for odd functions sometimes can give you the value of a definite integral when all other methods fail. So, for example, think about the integral from minus 5 to 5 of x cubed cosine x dx. Now imagine you were trying to use the fundamental theorem of calculus part 1 to work out this definite integral. You would start to struggle to find an antiderivative of x cubed cosine x. Sure, you could find an antiderivative of x cubed easy enough. You could find an antiderivative of cosine x easy enough. But there's no product rule for antiderivatives. You'd be hard-pressed to find an antiderivative for x cubed cosine x. So in evaluating this integral with the fundamental theorem of calculus part 1, you immediately come up against a roadblock because you can't find an antiderivative. But if you look at this integral, it's the integral from negative 5 to positive 5, just like this. And furthermore, this function x cubed times cosine x, remember, that's an odd function. So we know that for an odd function f, the integral from minus a to a, f of x dx is 0. And that would tell us right away that the answer to our question here is 0. So there are a few examples of these problems in the book. Take a look at those. This is not the most important topic, but especially if you go on with calculus in subsequent courses, and also from time to time in this course, these properties will turn out to be very useful. We're moving on to our fourth topic for today, average value of a function. This is one of the applications of definite integrals that we're going to look at. And the question is this: what is the average value of f of x on an interval from a to b? So here's a graph of f of x defined on an interval from a to b. And I've scaled the y-axis from 1 to 6, so you can kind of estimate the function values for various values of x here. But we're saying on average, what is the value of f of x if x is between a and b? It's sort of like asking on a given day, what's the average temperature? It makes sense, but it's also kind of a tricky question because what is the average temperature? There are infinitely many temperatures that you had on that day. And what's the average? Well, you add up infinitely many different temperatures and divide by infinity. It doesn't seem to make a lot of sense. Yet, as we're going to see in a moment, that's precisely what definite integrals do. So think about this question. What is the average value from a to b of this particular f of x when x is between a and b? Given that there are infinitely many values of x between a and b, and you can't add up infinitely many numbers, you might want to think about taking a bunch of sample points, x1 through xn, and go ahead and make them equally spaced. Why not? So they're spaced a distance of delta x, which is b minus a divided by n, apart, just like in our setup for the definite integral in its definition. And what you could do here is just take f of each one of these sample points, and you've got n sample points, so you'd add up f of each one and divide by the number of sample points you have, which is n. So the average value of f of x when x is between a and b is approximately equal to the sum of the f's of all of these sample points, f of x1 plus f of x2 plus f of x3, all the way to plus f of x sub n, right there, divided by the number of samples that you have, which in this case is n. So this is just an approximation so far, just an approximation. But it makes sense. You could get a pretty good idea of what the average value of this function is by doing something like this. Now, simplifying that, using sigma notation, the top is sum from k equals 1 to n f of x sub k. It's all divided by the n. And I'm going to twist this around in a way that's going to be really convenient for us. I'm going to insert a b minus a, one of them here and another one on the outside of this sum. So they actually cancel out. If you bring the b minus a here outside of the sum, it'll cancel out with this one. And the n that was down here, I'm just going to put it under the b minus a that's inside the sum. So you got to look at that for a second, but you'll quickly convince yourself that this equals that when you distribute the 1 over n into the sum and insert a b minus a on top and also bottom so they cancel out. Now here the b minus a divided by n, that's delta x. So I'm going to write this by replacing the b minus a divided by n by delta x. So here we have an approximate average value of f of x on the interval from a to b. It's equal to 1 over b minus a times the sum from k equals 1 to n of f of x sub k times delta x. And this is interesting because if you look at the sum here, forget about this fraction 1 over b minus a, but just look at that sum. That's a Riemann sum. It's part of the definition of a definite integral. So average value is, in some sense, mimicking the structure of a definite integral. Now, we haven't answered our question yet because this is just the approximate average value. You've taken some sample points. You really haven't considered what's happening between these sample points. And for all we know, we might have been really unlucky with picking these sample points. It could be that maybe those were low points on the graph of f of x. I mean, for all we know, the graph of f of x might really have looked like this, right? Kind of going up and down. And we were really unlucky with our sample points, and we picked little local minima for them. And from these sample points, we're missing some of the high points on the graph. So you can see that this average value, it could be pretty far off from this approximate average value might be pretty far off from what you would expect to be the actual average value of f of x. Here, it's probably too small. So what are you going to do? Well, I guess the obvious answer is just to add more sample points, make them more of them and closer together so you can pick up these high points as well. So if you want to get it exactly, just let the number n of sample points in this expression go to infinity. Take the limit as n goes to infinity of this expression, and I'm going to move that limit inside this constant of 1 over b minus a. So you get 1 over b minus a times the limit as n goes to infinity, sum from k equals 1 to n, f of x of k delta x. Now, this limit, you'll recognize that as the definition of a definite integral. That's the definite integral from a to b, f of x dx. So that's an answer to our question. What is the average value of f of x on the interval from a to b? Answer, the average value is exactly 1 over b minus a, integral from a to b, f of x dx. So it's kind of interesting that this definite integral, as you can see here, it really is literally adding up infinitely many terms, infinitely many f of x values, as n is going to infinity, and dividing by infinity, and coming up with a meaningful answer. Now we're going to go on and look at an example of this in just a moment. But I want to call one thing to your attention, and this is a very important point, and it will especially be important if you go on to further study in mathematics. Remember how we set up the definition of a definite integral. It was in terms of a limit of Riemann sums. And by we had the fundamental theorem of calculus part 2, which gave us a shortcut way of evaluating that definite integral that bypassed the limit. You might ask yourself, why do you need the limit then, if you can always get the answer without a limit? Well, the answer to your question is this. The limit definition of a definite integral gives it its meaning. Look at what we did here. We set up this problem in a way that had some Riemann sums in it, and in a very meaningful way, we took the limit as n went to infinity of those Riemann sums, and we passed to a definite integral from the definition of a definite integral. Notice that if you had forgotten that the definite integral is defined this way in terms of Riemann sums, you never would have gotten the formula for average value. You really need that limit definition of a definite integral in practical applications. And you see that happening here with average value of a function, and you're going to see it happening over and over and over again in all kinds of other different contexts. That limit definition of a definite integral is crucial. That's what hooks real-world problems to the theory of the fundamental theorem of calculus, part 2. So keep that in mind for future reference. Let's look at an example. I'm summarizing what we just figured out. The average value of f of x on the interval from a to b is 1 over b minus a, integral from a to b, f of x dx. For an example, let's see if we can find the average value of f of x equals sine of x on the interval from 0 to pi. So here's the graph of sine of x, and we're looking for its average value when x is between 0 and pi. So certainly there that average value looks positive. But what is it exactly? Well, we could use this formula to find it exactly. But before we do so, I want to kind of guess. If you think about a y value that might be the average value of sine of x, you play around with raising and lowering a horizontal dotted line like this, and somewhere around midway between 0 and 1, you get to a point where it seems to balance out that the times that values of x where f of x is lower than that, and the values of x where f of x is higher than that dotted line kind of balance out somewhere around 0.6. I know that's kind of hazy, but you might guess that the average value of this function, sine of x, on the interval from 0 to pi might be somewhere around 0.5, 0.6. Just a guess. Let's endeavor to find it exactly. What we could do is use this formula for average value. B is pi, a is 0, and the f of x is the function sine of x. So the average value, according to our formula, is 1 over pi minus 0, integral from 0 to pi, sine of x dx. And here we can use the fundamental theorem of calculus. To evaluate this definite integral, we need an antiderivative of sine of x, which is minus cosine of x. And the fraction 1 over pi minus 0, that's right there. And so 1 over pi times minus cosine x from 0 to pi. And that's 1 over pi times minus cosine of pi, then minus cosine of 0, where you plug in the 0. And let's see, cosine of pi is minus 1. Cosine of 0 is positive 1. So we're getting 1 over pi times minus 1 minus 1. And that's 2 over pi. And if you take out a calculator to check, that's approximately equal to 0.636619. And it certainly supports our guess, our supposition, that the average value was somewhere around 0.6. Well, it's precisely 2 over pi. That's it for today. Our next lecture, Lecture 45, will be on the so-called substitution rule. It's a new integration rule that gives a way of evaluating more complex integrals. I'll see you then. Goodbye.